Good afternoon, everyone. Thank you for joining us for the first virtual Friday lunch of the semester with CSAIL Srini Devadas. I ask that you please send me any questions for Srini throughout the presentation, and I will ask on your behalf. So without, during the presentation or after the presentation, whatever you're comfortable with. And so Srini, please feel free to take it away.
Awesome. Thanks, Matt. And let me know if there's glitches. Suddenly you can't hear me, or my slides aren't advancing at some reasonable rate. It probably means something went wrong, but I think it's unlikely. Yeah, hello everybody. Good afternoon. I'm Srini Devadas. I've been at MIT for a long time. This is year 34. For 20 years or so, I give talks on hardware security. And I'm going to talk to you today about really pretty recent work. I mean, I'd say maybe 6 months total from when we started working on it to now on private learning and kind of a different approach to private learning. I don't have slides talking about extant approaches, but I do want to spend some time on, I would say, competing or certainly, in some cases deployed and strong approaches to private learning. But this talk is on an approach that we want to really push in terms of trying to figure out what we can do with respect to the privacy properties that we can provide when we obviously we want to do private learning. So there's a privacy property. And anytime you're doing transformations on data, there's always a question of how accurate your learning is going to be, because your data is not your original data. And so primarily this work has been done by Hanshin Xiao, who was a PhD student in my group. And we're also collaborating with Elaine Shi of CMU, but this particular talk it predates our collaboration. Motivation. We want to outsource computation on private data. We want to do things with private data, like learning models on it, maybe doing regressions on it, just getting some simple statistics on it. Obviously, a huge area, lots of work, thousands of papers, and computation got replaced by learning. And then there was, even more papers that were and more interest, and that this has happened over the past few years. Obviously, computation on private data is much older than that. I mean, it's MPC and approaches like FHE, at least in terms of concept, are 40 years old. So there's 3 dimensions here with respect to the main questions, if you will. The questions relating to these 3 dimensions are, all right, you claim that you're doing private learning, you're sending your data, your ciphertext, if you will, your transformed data over to a server. And what is it that the privacy guarantee, what is the privacy guarantee you're giving? Now, it could be, differential privacy, it could be a computational security guarantee. In the case of differential privacy, it's information theoretic. You're saying if one of the data elements was replaced, you would not see any change in the utility, and therefore you have a privacy guarantee. In the case of fully homomorphic encryption, there's usually some sort of lattice problem that is considered or assumed to be difficult, and that's your security or your privacy guarantee. In the context of GDPR and CCPA and things like that, one is concerned about whether these privacy guarantees conform to the law of the land. I won't say much about that in this talk. So that's one dimension. The other dimension is what is the computational cost of private computation? When you take MPC approaches or FHE approaches, you're working in a transformed domain. In the case of FHE, the ciphertext is a billion times bigger than the plain text, roughly speaking. And so obviously the cost of private computation is significant. In the case of DP, probably not. But then the third dimension, the third question is, what happened with respect to the utility of your private computation results, or the accuracy of your private computation results. FHE and MPC, they have this operation by operation equivalence. You get exactly the same thing, after every add, every multiply. Obviously, in differential privacy, you're perturbing the data. And the sad fact in differential privacy is that in order to get a strong privacy guarantee, you have to appreciably perturb your data. And when you appreciably perturb your data, usually your accuracy suffers. And certainly there's special contexts and special cases where you can try to get a better trade-off. Right? So those are the three dimensions. And we're trying to hit on all three of them. You want a strong privacy guarantee, you want minimal overhead of private computation, and you want your utility to be exactly the same as with the plain text or the unencrypted computation, non-private computation. And as I said, there's many approaches with different trade-offs. I won't belabor the point, but the fact of the matter is that there's nothing out there at this moment in time that gives you all three of these in sort of in an optimal way, in an ideal way. And so that's why this is still a research problem. And lots of people are working on it, including in my group. And so outline for kind of the technical part of this talk, in the sense that, or the research, part of this talk, what have we been doing here that that is new, is we have a transformation-based approach to learning and optimization, where we're doing a one-time uniform transform. So there's relatively few approaches that do that, and we have one. We call it the dauntless approach, and I'll tell you why a little bit later. It's an acronym, and we've proven information theoretic security properties for this framework. That's still an ongoing process, but we certainly have a theorem or two, and I'll share with you. And one of the nice things about this approach is it generalizes to kind of an even harder or problem or a different setting, where there's multiple data owners, and they are not necessarily adversarial, because they do want to work with each other to collaborate and get a better model. Some people call it the consensus model, and federated learning, certainly attempts to solve this problem, which is, hey, let's collaborate and get a great model corresponding to our aggregate data sets. But I'm precluded from sharing my data with you. In fact, you're as bad as the adversary with respect to the leakage of the data because of the law of the land, or because I don't trust you. But together we'd like to get something that's better than what we would get if any single one of us just worked on our data and got a model or got a regression result or what have you. And we have some results, preliminary empirical results, in addition to the theory results that I'll share with you. And so just sort of a top level, we're trying to solve an optimization problem, a learning problem. There's a bunch of samples. This is a supervised learning. In the training, you have labeled samples. X is the data item. It could be an image. Y is the sample. I'm sorry, Y is the label. It could be the cat. It could be a cat, or it could be a dog, or what have you. And you're trying to conceptually minimize generalization error. And usually there's a loss function, and all of these things, the loss functions vary significantly. But here's the L2 norm of corresponding to a generic loss function. And usually what happens is learning measures empirical error, this equation that you see below. And this is machine learning 101 or 001 for people. And I just want to give this as context because I wanted to talk about transformed learning, where what we're going to do, and the only difference between this equation and the previous slide's equation is this t over here. Don't know if you can see a cursor, but you have f of t of x. And that is essentially what the transformed approach would be, that you take the entirety of your data set and you transform it We're going to leave the samples the same, though you could apply a different transformation to the samples. That's not part of this talk, but let's assume that you're okay with exposing the samples, and you're going to transform your images or your financial data or what have you using this transform T that is going to be the secret private transform. And you're going to apply that uniformly to everything, right? So kind of a basis for discussion or the basis for extrapolation is this observation that let's assume T is bijective, and you have a unique optimum. So the T being bijective is not a strong assumption because we can certainly choose T to be bijective and invertible, but the problem having a unique optimum, that is a strong assumption, but bear with me. Then the fact of the matter is that if you had an all-powerful learning method that can find this unique optimum, then you can basically go backwards. Once you've done this transformed learning, the T of X is gone off onto a server, all that data, and then this all-powerful learning method discovers this unique optimum, and then you get back this model, which we're calling FT star, which is this optimum model on the transform domain, and you can certainly use that to solve your original problem, right? By essentially taking T inverse, and you can do that because T is bijective / invertible. And so that's kind of a basic observation, and that under an arbitrary bijection transform, which you can choose and you can keep secret, an equivalent optimal model exists. So we can view T as a key and T of X as an encryption procedure. And so each of your private samples is you apply T to it, and that's where you get your transform samples from. But the difference between this and encrypted computation kind of from the cryptography world, a la FHE, fully homomorphic encryption, is that we're not really asking for an operation by operation equivalence between the encrypted and plain text computations. In FHE, you do an add on the ciphertext, and if you decrypted that sum, it would be the addition of the two plain texts. And then after that, if you did a multiply, same thing. Here, we're saying, look, the path that the learning method on the server takes to this optimum or an approximate optimum could be whatever. We're just asking for, we're hoping, empirically speaking, that path is going to lead us to an approximate optimum or pretty close to the optimum. And we're only going to verify that, to be completely upfront, by running experiments, right? And maybe there's some strong assumptions you can make about convexity, and in the case of linear models, you can probably prove that, and not probably, you can prove that you will get the optimum. But in the general setting of deep learning and complicated nonlinear optimizations, you can't say much, and that's kind of true even in the plain text world. So it's not like that we can lean on some great result outside of making assumptions about convexity or strong convexity or what have you. But the key, of course, is that we want to be able to show a security result, a privacy result, because otherwise, you basically have nothing. This framework, which you can see, it's an acronym. We use some data augmentation, which I'll get to a little bit later. The key is that there's a uniform transform T on the data. So every sample gets transformed using T, this private transform, and it's as simple as multiplying by an invertible matrix, or it could be something a little bit more sophisticated, like passing through a neural net with random weights, and then this transform data goes over to the server. The server is going to train on this transform data, and we're going to get this model F that is going to get sent back to the user. And there's a couple of ways you can think about using this model F. Perhaps the easier way is down at the bottom, where once you get this model and you have a new sample, X new, then you run your private transform T on X new, and then you query the model with this transform sample. So if you just did F of X new, it would get garbage, because this T is going to dramatically change your data. It might maintain some properties of the data, but it's syntactically it's going to turn your data into garbage. And so if you just apply X new without T to the learned model F that was learned in the transform domain, you would not get interesting results back. That's sort of the easier way to explain it. Like I said, the other way that you could do it is you could compose F and T, and then just create a model from that using this composition. They're basically equivalent. And then you have your model, and you can forget T if you want, because T is essentially been embedded into F. And then you get this new thing that is your reconstructed model. So that's the game here. So hopefully not too complicated. There's lots of challenges, right? So now TFX only carries information at the sample points. You end up with, obviously, learning algorithms have limited learning capacity, and that's a problem. So, and it's possible that you're losing information. So if you have a very nonlinear transform, I mean, if you put a one-way hash function on X, I mean, good luck, right? I mean, you're going to get nothing that's interesting out of this learned model. So you have to worry about that. That's a challenge. We're doing a uniform transform. You can think of this as multiple encryptions with the same key, and that implies the composition of privacy loss. And therefore, you know, there's a chosen plain text attack, and I'll spend a bit of time explaining what that is and how we kind of avoid that, and what our assumptions are with respect to security in the context of chosen plain text attacks. And what you really want is a trapdoor, and this is, you know, seems hard to get, which is you know, T is going to transform your data such that the adversary, when they look at the transform samples, they you can't discover the private samples, but somehow there's enough information in T of X such that you get good utility, right? So that's the crux of the matter. So what is this transform? So I'm going to only talk about a very simple transform that is illustrated in this on the slide, where let's say I have an image of a cat, which is square root of D times square root of D. And so that's, let's say, 100 by 100 pixels. And then you end up getting a row vector of 10,000. So D is 10,000 here. And that's our row vector. So this is not to scale or anything like that. And then we're going to go ahead and multiply this row vector and any of these samples. So my private samples are this cat and this dog out here. And I'm going to multiply it by my T, which is a multiplication by W. So that private transform is a multiplication by a random matrix. That's a D times D matrix that has elements 0, 1, and -1 in it. And there are many variations here, but this is the one we'll go with. And then you end up, you know, getting this random looking image out there. Again, this is not meant to be accurate in terms of what the actual numbers are, or to scale, but hopefully you get the picture. Obviously, this is a very global transform because you're doing matrix multiply. You have a 1 times D row vector, multiplying it by this giant matrix, and then you get another 1 times D row vector. And there's a lot of mixing here. And take it from me that if you do this with a random W, that, you know, certainly cats look nothing like dogs, and vice versa, and they all look pretty random at the end of it. Right. So that doesn't mean, obviously, that we have a security property immediately, but it definitely, you know, is a start. Right. So that's our random linear transform. You could do more. You could do more matrix multiplies. You could do a little nonlinearity, but we'll go with this, and we'll assume that W is invertible because that actually increases the stability of learning. That's actually not essential, but let's assume that. And so let's take a look at this chosen plain text attack, where I have a data set of n samples. And so this is n samples. Each of them was 1 over D. So I end up having this n times D private samples. And then I'm multiplying it by D times D matrix. So obviously, I'm getting n times D. So unlike in FHE schemes, the size of my transformed data set is basically the same as my original data set. And the assumption here, I mean, the vanilla assumption here is that X is private. So X is this entire data set of private samples. Obviously, W is private because I've chosen the W as a private transform. And then, but I'm exposing X times W, right? So this is shown to the adversary. And so now if you actually use, I'm sorry, let me go back to that. If you actually used public samples and the adversary knows the correspondence, then all the adversary needs are D samples, so D images, Then there's a simple linear, obviously system solution that is going to get you your W. So so these samples and correspondences, the known samples and known transforms, that is going to break your scheme, right? So that's certainly the case. Of course, the whole point of this was that I had private data and I wanted to learn on private data. So there was some entropy in X. Otherwise, what would be the point of even transforming the data? If there's no entropy in X, then send the X over to the server, and the server doesn't learn anything additional because there was no entropy on X, and move on, right? So what we want to characterize is how does entropy in X give you a privacy property associated with this scheme? And the adversary could have partial information. So there's a game here with respect to what you're assuming about the prior knowledge of the adversary and how much entropy there is. And we want to relate kind of the prior knowledge of the adversary and obviously that implies entropy in the private data, assuming the adversary does not have complete knowledge. And obviously you have private W and you're exposing the X times W. And can you say something about this being difficult to reverse, to discover W, or to discover the X, or sort of take away the entropy of X, if you will. Yeah, so hopefully that was clear. The framework that we're going to use is Pac Theory, probably approximately correct theory, and Pac inference and Pac inference resistance. And it's given an observation, how much information can an adversary recover with respect to the private data? And so can an adversary approximate with error smaller than epsilon the input with confidence at least 1 minus epsilon? And this is really the kind of the way Pac theory uses its basic definition. So there's epsilon and delta here, and for you differential privacy aficionados, they're actually reversed from differential privacy in that here you want epsilon to be large for strong security, because then that means that you can't approximate as an adversary well. It's a loose approximation, and looser for larger epsilon. And you also want your delta to be large in that you want the adversary's confidence to be low. And so I just put that out because sometimes people get confused when they see the epsilon and delta, especially if they've lived in the differential privacy world. So overloading of symbols, but they're conceptually different in meaning and in terms of their scale, if you will. And so there's just a definition here that really doesn't say a whole lot, honestly, which essentially says, look, I mean, I got a mechanism, and in this case, we're multiplying by a random matrix, which is 0, 1, and -1, and it's a D times D matrix. So that's our mechanism. And now I'm saying, I'm asking for a theoretical result that says, hey, can you say something about Pac inference resistance with respect to this mechanism, assuming that the adversary can see these transform samples, and you're probably going to have to make an assumption about the private input data. I mean, it's from a distribution P, and that's going to capture the adversary's prior knowledge, but obviously the statements about that distribution turn into different assumptions for a theorem and potentially different results. And bottom line is you're saying, hey, I don't want the adversary to be able to closely approximate with small epsilon my private samples with high confidence. So either make sure it's low confidence for the good approximation, or it could be high confidence, but for a bad approximation. And you'd be hovering around 50% or what have you for the confidence, and epsilon should be pretty large. The cat should look, the recovered image shouldn't look like a cat if the original image was a cat, right? It's okay to look like a dog, or be a dog's image if the original was a cat. And so a little bit more setup, and then the main result that we have, or the one that it's changed really in the past few weeks, but we'll call it the main result, which is the way we do this is by assuming a computationally unbounded adversary. So we're in the information theoretic world. We're going to assume a computationally unbounded adversary, and we're going to essentially say, look, the number of samples that the server sees, that number of transformed samples, might be, let's say, 500,000. But according to our theorem, given our assumptions about the entropy on the private data, for a particular epsilon on delta, the adversary needed to see 1 million samples or more. So the M here is 1 million in order to get a reasonable approximation of the private data. Right. So that's kind of the whole deal here with respect to what we're proving. And again, based on different assumptions, there's different results, different proofs, but fundamentally it ends up becoming a lower bound on the sample complexity for recovery. And there's some parameterization, just like there is in the DP world, with respect to the epsilon and delta relating to the entropy of the private data. And so here's one result, right? So let's choose W to be a 0, 1, -1 random matrix. We're going to take our data set and we're going to multiply it by W, right? And maybe there's some number of samples. We'll just call it 1,000 samples in that data set, and the transform data set is exactly the same size as I said before. Now let's make a simple assumption. So this is one result that says that the prior knowledge that the adversary has on X is that it is a multivariate Gaussian distribution with some variance, and that's tau, right? So the greater the variance, the greater the entropy. We can show a result that essentially says this mechanism that we have, which is multiplication by a random matrix W, satisfies epsilon delta Pac security if the number of exposed transform samples is less than this constant, which we can parameterize, times the dimension D, right? So C is going to be a function of epsilon and delta and tau. So usually if you allow for a smaller epsilon, which means a better approximation, C is going to increase. If you allow for you're asking for very high confidence, which means delta is small, C is going to increase, and C is also going to increase if the entropy in the private data is large, if tau is large, right? I won't give you the equation because it's fairly hairy, but just as an example, if you set things as shown here, you end up with C of 31.5. So with a 51% confidence, the adversary cannot approximate to within 0.2 of square root of D with respect to epsilon, provided the number of exposed samples is roughly 30 times the dimension, right? And so this is an amplification factor, to be clear, that comes from the entropy of the data, because remember that the chosen plain text attack with the 0 entropy only needed D samples. So now you have this 31 factor that came from the fact that you're using the entropy of the private data. So the chosen plain text attack means no entropy, because the adversary knows the entirety of what was transformed, and they see the transform samples. So it's easy to get the private transform back. So that's kind of where things are at. There's a bunch of other results, but I won't bore you with it. Simply because I think this is the essence of it in terms of the argument. You can also obviously run empirical attacks on the transform samples. We've certainly done some experiments on running generative adversarial networks on the transform samples and doing some guesswork to try and go back. But in the context of the assumptions that we make and the entropy that we make, these theoretical results should hold. And they're certainly validated to the extent that we run these experiments by these GAN experiments. And so one question that you might have is, well, what if you wanted to use public samples? So this chosen plain text attack seems kind of annoying, because you got to have some entropy in your private samples, each of your private samples. If D of your samples had 0 entropy, you're dead. Well, you can always add entropy even to public samples. And one very established technique of data augmentation that was obviously not from us, since well, we don't do well, it wasn't clear if that was that was obvious, but it certainly wasn't from us. which is mix up, which is a very kind of neat and neat, cute technique that essentially says, I'm going to be able to mix images together and change the labels and create these composite images and have different labels associated with them. And by the way, this improves utility in some cases, because if you had a small amount of data, you can expand the data. It's a data augmentation technique. We want to use mix-up for privacy, and we use it in a particular way that I'll describe to you in just a second. But as you can see from this picture, this is what you might get, out of mixing a cat and a dog. And no one is saying that you can't recognize, the dog from this picture or the cat from this picture, this mixed up picture. That's not the privacy, requirement here, or the privacy guarantee here. Remember, we're going to take this mixed up picture and we're going to multiply it by a random matrix. But this is a way of augmenting your data. And let's say, for argument's sake, that the cat image was private and your dog image was public, or vice versa. Then you're adding some entropy to your samples. Each of the samples that is being transformed has a little bit of entropy in it, because some of the parts of those the images that were transformed were private, right? So this is just a way of using a bunch of private data to create a lot more samples that all have a little bit of entropy in them. And obviously, you're not increasing entropy, but you have more samples, each with a little bit of entropy, which precludes the chosen plain text attack. And you can keep lambda secret if you want. Obviously, the correspondence with respect to the exposure of the cat in the transformed image and the dog would be public. Some of this has to be kept hidden, because otherwise you lose all your entropy. And so some really preliminary results on kind of the simplest examples first, and one of the set coming up. MNIST is, well, I guess the first thing that you run on any of these new schemes. It's a trivial data set by today's standards, 60,000 images. You can do really well with a whole slew of techniques. And in non-private training, you get, let's say, 98.5% in for the 60,000 samples using a fully connected network. So that's the first thing that you have here. And then let's say you ran mix-up. Not clear why you would do mix-up for something as simple as MNIST, but obviously if you want to use mix-up if you need to increase, well, to make sure that we are protected against a chosen plain text attack. And so if you do that, well, your accuracy certainly roughly stays about the same. And you can see these numbers in the next two rows here. Now the fun starts. You take the mixed up samples, or you could also do this for the private samples, the original samples. But let's say that you did that for the mixed up samples and you transform the data using the W matrix. You end up maintaining, in this case, you end up maintaining the utility. And assuming that there was some entropy in the MNIST data, so you hid, the MNIST data is public, of course, but let's say you added some more data to it, or some of those weren't exposed. If there was a small amount of entropy in that MNIST data, then you would be able to say that even though the transformed samples were exposed to the adversary, the adversary would not be able to discover these private samples, right? So you have to think about MNIST as, let's assume that the entirety of the data set wasn't public. Let's say a tenth of the data set was private. You could use that tenth of the data set to create mixed up images, and then you could transform those images. And this chart, doesn't tell you that process, but it tells you that if you use mix up on transformed images by multiplying with W, which is a pretty dramatic transform, you're not losing utility to the first order, right? That's what this chart tells you, nothing else. Now, let's say that you did something more interesting with CFAR, and you still used a fully connected network. Then same thing. You can track what you get with the non-private training. So you have the original 50,000 images. You get 55% on the fully connected. And then if you do the mix up, you get kind of close. Not it gets a little bit worse, even though you're using more samples. And then you do the private transform, which is the bottom here, and you're essentially approximating what you get with the mix up on the non-private case, right? And your reaction to this slide should be, goodness, these numbers are they're as close to each other, but they're all uniformly bad. And that is absolutely correct. I mean, you're using a fully connected network, and it doesn't do well on the CFAR data set. And our transform was essentially a global matrix multiply. And all this tells you is that, well, the transform is going to give you close to the accuracy that you would get if you ran a fully connected network. But you should be running a fully connected network on CFAR because there's so many better techniques that you could use, including CNNs and transformers and so on and so forth. Unfortunately, if you use CNNs and on transform data using exactly the same random matrix transform that I described to you in the way that I described to you, which is W1 matrix, multiply the image, send it over to a CNN, well, then this chart would look a lot different. The non-private training would get you 90+%, and the transform training would still only get you 50%, right? So that's obviously untenable. I mean, this is not something that is worth putting a chart up on, though I did give you a sentence on it. So what do we do when we have CNNs? Well, the good news is that we can tailor a transform to mimic the sliding window of convolution, and it's still a matrix transform. It's just going to be a transform using many small matrices, and it's going to have a security property that's basically essentially the same as the property that we had before with respect to the information theoretic sample complexity bound. And you can get now your utility to kind of approach the utility of non-private data, right? So this is obviously it gets more interesting than what we had before with respect to fully connected networks, right? And so what does this transform look like? Well, it's going to, as I said, be a multiplication, but a multiplication of many small matrices, using many small matrices to multiply the original data set. So if we're going to do sort of a pretend convolution where we have a k by k convolutional filter, so k could be 3 or 4 or 5, it's a small number, and then we have our image, which is square root of d times square root of d, and we're going to slide this this filter across the image. That's exactly what a convolution is. And every time we slide, we shift over t pixels, and t could be 1, or t could be 2. I mean, that's the parameter, right? So you see these three numbers here, k, t, and d, or square root of d, and they're all should be familiar to you if you know what a CNN is, or if you know what convolution on images look like. And so you keep doing that, and you're going to go through this entire image just like a convolver would. And each time you do this, you can look at essentially what the image pixels are that are being grouped together. And there's k by k pixels, k square pixels. Let's now turn that into a row vector. Just pretend that it's a row vector of 1 times k square, right? So k by k turns into k square. That is our input image, which is xi. And I'm going to, every step that I do this convolution, I'm going to multiply this 1 times k square row vector with a k square by k square random matrix, right? So there's it's not the same matrix, it's a Wi matrix. So there's a different matrix every time I step through this convolution, right? So the way I'm going to transform my input data is to do a pretend convolution on the input data, where I'm going to choose my k. I don't have to choose a convolutional filter here. This is not what's happening. I just choose k, which is the size of the filter. I do this pretend convolution. Every time I see a sliding window, I get a 1 times k square row vector. I multiply it with this randomly generated Wi, and then I get my transform data, which is zi shown on the right. And so in the x dimension, I'm going to step through q times, and this equation you can verify for yourself. And in the y dimension, I'm also going to step through q times. So I'm going to end up with q square of these multiplications with this k square times k square random matrices, right? So let me say that once more, or actually, let me just show you what it looks like here. I have Q square random matrices, the W1 through WQ square. They're going to multiply each of these sets of pixels corresponding to X1, which is K square pixels. Obviously, there's some commonality in the pixels here. That's okay. And X2 and so on and so forth. And so that is my transform data. So on the client side, I've done a multiplication. It's a little bit different from before, but hopefully you understand what that is now. And then I take this transform data and I'm going to send it off to the server. And I'm going to modify the CNN on the server side ever so slightly, where I'm going to prepend to the CNN another layer that you can think of as Q square small fully connected, K square by K square layers, where each of these EI matrices are learnable weight matrices. So these are matrices that have unknown weights, and they're going to be learned through the CNN learning process on the server side. And then the rest of it kind of looks the same. We're not really making a modification on the CNN. We're just prepending, as I said, this thing over here. And why are we doing this? Well, we're doing this because we want our first layer of the learning network to look a lot like our private transform. And we want to kind of, quote unquote, cancel out this private transform. Obviously, we're not going to get the inverse of this. If we could get that, this thing would be broken. But we want there to be kind of there to be a transformation that is similar to the private transform, the inverse of it, I should say, as opposed to doing a convolution immediately, which essentially doesn't function very well if I took the original data and I multiplied it by this giant random matrix, because I've mixed too many things up. It's not a local convolution. It's like a convolution with a filter that's as large as the size of the image, which doesn't work very well for visual recognition tasks, right? So if you do this, then things get a lot better. Not necessarily optimal or anything like that, but now you're in a situation where if you got 93% for non-private training, then you get close to 90% for the private training, which is this transform with this random matrix. And as you can see, it doesn't take much longer to run the private training versus the non-private training. That was true even in the prior experiments, because your data set size is about the same. It's obviously there's some change in the data, and this is all things that probably required lots and lots of additional experimentation. And as I said, we haven't been working on this very long. This is sort of a one-shot deal with respect to the first set of experiments that we've run. So in the time that I have left, I just want to tell you how, very quickly, how this generalizes to collaborative learning. And you can do collaborative learning using multi-party computation, but we'd like to do things that are a little bit more lightweight. And there are a couple of ways you could do this. Let's say that Matt and I want to aggregate our data sets, but in a private manner, and do learning at the end of it and get an aggregate model. Well, we could use a multi-party computation to decide on a transformation matrix that neither of us knows, and then use the techniques that we've described to you after MPC to do the learning on the server side. Now, this means that every time we want to query the model, because neither of us knows the transformation matrix, if any of us knew the transformation matrix, we could discover the other person's samples. So that is a no-no. But inference would also require MPC, because neither of us can know the transformation matrix. If each of us use different transformation matrices, well, this doesn't work at all, because I've taken two data sets, multiplied them by two different random matrices, aggregated them together, and you get terrible results. So that doesn't work. What you can do, and so let me just talk about this in a non-private setting. You could use a notion of task augmentation, right? That we think we've come up with and is novel, but we're not completely sure. But it certainly seems to work for us, as I'll describe to you in just a minute. What is task augmentation? Pretend that you have two data sets and they're labeled in this way just to differentiate them, but they're from roughly the same distribution. They're all images of animals. let's create a composite task that's kind of a cross product of these tasks. So x1 1 and x1 2, or x2 1 and x2 2, or x1 1 and x3 2, et cetera, et cetera. So you can do this cross product. You can choose some random groupings, and you can create this composite task. And you go off and learn this composite task that has a larger data input and a larger sample as well. So maybe you have a cat and a dog concatenated together, and then the label is cat, comma, dog. Now we train the model on this composite task, and then the way you run inference is when you have, let's say that owner 1 wants to run inference after he or she got the model back. Well, take x new, which is the new thing that you want to know the label for, and then concatenate that with something that came from owner 2. There's no privacy here, to be clear, at this moment. And then just get the label for that. And then if you want to do maybe a little bit better, you could certainly run inference with x new 1 and x1 2, x new 1 and x2 2, as shown here, and take the majority. So 2 of them are cats. One of them is kind of I don't know what, and you declared this to be a cat for x new. Right? So there was no privacy here because everything was exposed in terms of samples. But the beauty of the scheme is that if you do this, you are now allowed to have different transforms for owner 1 and owner 2. So from owner 1 standpoint, you choose a private transform, create your transform data set. Owner 2 chooses a private transform T2 and chooses and then creates a transform data set. Send those transform data sets over to the server. That's going to do this random regrouping on this composite task, and it doesn't need to know T1 or T2. It just takes what it gets and does the grouping, trains the model F on the aggregate samples, sends the model back, as you can see here, back to owner 1 and owner 2, so they have F. And now if owner 1 wants to do inference on a new sample, well, they just run T1 x new on their new sample x new, and they don't need the original samples corresponding to owner 2. They just need the transform samples. In fact, it's exactly the transform samples that would work here because F is being learned on the T1, T2 samples. So they could just concatenate and do the inference just like they did before. And so the private setting and the non-private setting are identical in the context of task augmentation with independent choices of T1 and T2. And you didn't have to do multi-party computation or anything like that, right? And the security is exactly the same because T1 and T2 are randomly selected by single parties, right? And so if you do that really quickly, you don't look at the numbers, just listen to what I have to say, which is you can do a little bit better from the setting where owner 1 samples gives you X%. If owner 2 samples are added in this task augmented way with the privacy, you can do a little bit better than that. But you do lose with respect to the non-private training. And so if you were able to just aggregate the samples with impunity, without worrying about privacy, that does better than this multiplying by T1 and multiplying by T2, right? And so, as I said, these are early days yet. This is the first set of experiments, but it's an intriguing idea that we'd like to follow up on. So let me finish up. So the transform approach to learning, well, we hope is transformative. I was going to say transformative, but I meant to say transform. Your transform data approach is something that does not require an operation by operation equivalence of encrypted and plain text computations. We just start tossing over transform data, letting the learning or the optimization do whatever it did, and then relying on the distribution of the sample space to get utility of the models. And obviously, for this reason, they can be more efficient. The big challenge continues to be how we can get a strong security property for this. And I spent a bunch of time on it, and there's still more work to be done. The randomness here is multiplication by a random matrix, not additive noise. And in our view, it doesn't directly impact utility. Just because W is more random doesn't mean that, and it has larger entries or something, it doesn't mean that utility is automatically worse. Whereas if you added more noise in DP approaches, utility almost always suffers. So lots of open questions. Can we tailor machine learning algorithms to work better on transform data? We've been using these as a black box. Is there a transform with a computational security property? Can we do something more general? This is far away, where we are doing approximate computation, not just optimization, right? So let me go ahead and kill screen share, just because then if people want to turn on their videos, I can see them. Let me see if there's questions on the chat. This is just Matt putting up questions, and happy to answer questions on audio or chat. So I think we did okay, right? Okay, a little bit over, but yeah.
No,
So.
That was great, Srini. I do have a question, and anyone please feel free to add your questions in the chat if you have them. I was wondering if there were any industry sectors in particular that you think could benefit from this research.
Well, I have a generic answer to that, which is the medical and the finance sector, just because I think there's laws that preclude collaborative exchange of data. Things have to be anonymized. But I think generally speaking, I guess I think of this as being there's pillars associated with encrypted computation approaches, an MPC, and there's a pillar associated with differential privacy. And obviously these are used in the medical sector and the financial sector, and there's thousands of papers written. And this is a little bit of a different approach, and this is very, very far away, maybe decades away from, and maybe never will turn into a pillar like that. But that's sort of my generic answer, which is early days yet. Everywhere that these things are applied, we're not competitive at this point, but we would hope to be competitive. And in certain contexts, because utility suffers too much in the DP context, or it's too expensive in the FHE context, maybe this would get, this would slide in. But we would have to convince, I think, the cryptography community. That's kind of our goal here, to convince the cryptography community of the security formalism and the security properties that we're providing. And then the other side of it is more empirical. At least that's the only approach that we have right now, which is what is the utility of this? And when you change these W's, do you have guarantees? That seems difficult, but the fact that you're doing this for large data sets and other people are independently verifying empirical results would be helpful, right? So that's kind of where things are at, right? So someone raised their hand. Rohit, go ahead, and audio, or I think audio would work well. Right?
Yes.
Hey, Srini, thank you. That was a great talk. Quick question. So this could be great for sort of genomics privacy data. So essentially, as you look at trying to do genome-wide association studies across countries, how well would this scale to large data set sizes?
So I don't think there's a scaling problem, Rohit. I mean, I'm quite sanguine about the scalability of this approach, in the sense of I think the data set size didn't change. I mean, I said that I think once at least, but I want to repeat that. So that's a huge difference. You remember that the ciphertext in heavy cryptographic approaches scales by a billion, right? It's a billion, right? So and MPC is painful. I mean, just to sort of go through every ad, you're sort of doing crazy stuff. You're working on finite fields, right? There's nothing like that here, right? I mean, there's nothing like that here. So from a scaling standpoint, actually, that's the easiest question to answer. The scaling, no problem, right? The two harder questions, and I think we have a pretty good handle. Trying to get a handle on the security side of it, but I still think there's a marketing. We need to sell this security notion of Pac inference resistance and get it to be sort of validated, formalized, and agreed upon. And differential privacy took a long time to get to the point where it's now. Right, it took 15 years for it to be kind of reasonably well established in the cryptography community, and so I think there's going to be a process there. All right, then the other side of it is, which is I think is also I think doable, but also is going to require a lot of work, which is the last thing I talked about, which is what about, so going back to your question, so this also addresses scale. Okay, we ran CFAR, and sure I could run ImageNet, and you're talking about genomic data. What happens when you do large-scale experiments on this transformed data? So I think there's a big question here. And so if you want to help us answer that question, awesome, right? what would happen if you tried to do a large-scale genomic study? Forget the security aspect of it for a second. This is operationally completely doable in a matter of weeks, right? It just needs some effort, which is let's take this let's maybe do this vanilla transform. And if we have a transform for transformers, we have a transform for CNNs, we obviously the fully connected networks is the easy one. If you run this experiment where you're transforming the data in this way, I mean, it's 3 lines of code, in MATLAB, right? And then, what happens to the utility or the efficacy of that data? And it's possible, entirely possible, by the way, that my answer to your scalability question actually ends up being, oh, well, it ran, but you know what? The accuracy wasn't great and now we need to go back and look at this transformation that this matrix multiply, and maybe we have to choose it a little bit differently. And there's like a design space there, which I think is a cool research question. And I don't know the answer to that, but just computationally, I'm going to answer your question, I think, at this point. But
yeah, no, absolutely.
Tell me if I haven't.
I think just like a very quick comment there. One thing that would be great, and I'm not fully sure I've internalized the concepts you described, but things where you are anyways looking for approximate answers.
Yeah.
There, and this is basically what genome-wide association study is entirely about to a large extent. This would have the power where
you can't. I mean, you're absolutely right. I mean, there's a reason why we're doing learning here. I mean, I'm a security person. I know very little about machine learning, but because this transformation is inherently approximate, obviously, we moved into this domain, where, I mean, the DP is similar too, but and also you have approximation in aggregation studies, census and so on and so forth. So really, DP came in as an information theoretic approach, information theoretic security property, 15, 20 years ago. It has a utility problem. It's computationally very efficient. And this is, we're in that same ball game, right? So, like I said, it's early days yet. And it's possible that this entire thing is going to end up, being a squib, as opposed to, being an explosion in a good sense. But, that's the fun in it, right? So figure this out over the next few months. Yep.
Thank you.
Welcome.
Srini, we do have one more question if you have time.
Oh, I have time. Yeah.
Great. Theoretically, with the linear transform that you described, how can we reason the correctedness of the operation on the transform data, while in neural networks, the data will go through multiple nonlinear operations, which transforms the data and the linearity will not preserve?
Absolutely. Yeah, no. So when you say correctness, well, correctness is an approximate notion, just like we talked about with Rohit. So there's, to be completely clear, there's no correctness guarantee. But remember that the neural network, our transforms are looking a lot like a linear layer of the neural network. Okay, and except that when you actually choose weights of the neural network, that is, if it's a fully connected layer, that is the first transform that I just showed you. And then the weights of the convolutional layer is similar to the private transform. So we have some confidence in some intuition with respect to the utility being maintained, because we are tailoring this transform to look a lot like the layers of the neural network. And so that's why you get, I mean, this is the intuitive explanation for why this utility usually doesn't fall apart. I mean, the data looks dramatically different. I mean, because when you take an image, a cat image, and you multiply it by you linearize it, or you turn it into a row vector and you multiply it by this random matrix, it doesn't matter what you started with. You're going to you can look at random noise at the end of it. But the fact is, it was a linear transform. The fact is that a fully connected layer is doing that transformation on the weights, and that is what saves us here, right? So I don't know if that answered your question from a standpoint of theory, which I think was the do you have a correctness argument? I don't have that. I don't have a proof, but that's the reason why we think it'll work, and why we can tailor transforms to empirically validate that this transformation is going to give you decent utility. Just like, by the way, differential privacy folks add noise, and then they don't quite know what utility they're going to get is. They can say what the epsilon is. They can say this amount of noise for a variance in the Gaussian distribution or Laplace is going to give you a particular epsilon, but they can't tell you how much the loss in utility is going to be, other than running the experiment, right? Except in very limited cases. it's possible that we'd be able to do something in very limited cases, but not in, not if we don't make assumptions, strong assumptions, convexity, and so on and so forth. Hopefully that answered your question. Ask a follow-up, or email me if that wasn't satisfying. I may not be able to satisfy you, but happy to try again.
Thank you. Thank you so much, Srini. And I know we're past time, so I wanted to thank you so much for taking the time today to speak, and let everyone know that this will be recorded and will be on our website. So if you have any follow-up questions, if you're watching later, we'll feel free to connect you with Srini. And with that, thank you so much, Srini.